español y en inglés. Tenemos el gran honor y el gusto muy grande de tener nuevamente con nosotros al profesor Pierre Louis Lions, que viene del Collège de France. Viene por una visita muy breve porque tiene muchísimas cosas allá pendientes, entonces especialmente se lo agradecemos porque pues, es un esfuerzo muy grande que llegó ayer y se va mañana. Realmente es un esfuerzo que que nosotros apreciamos muchísimo. Pierre Louis Lions fue en la École Normale y estudió matemáticas, pero habiendo sido admitido a matemáticas en École Normale, él estudió las dos carreras simultáneas, física y matemáticas, porque siempre le interesaban las aplicaciones desde muy joven. Entonces, desde muy joven también empezó a publicar, su primer artículo también es en matemáticas aplicadas, usando técnicas teóricas muy fuertes, y toda su vida ha estado haciendo esto. En 94, él obtiene el doctorado en 79, y en 94, apenas 15 años después, obtiene la medalla Fields, así es de que es uno de nuestros medallistas Fields. No, sí,
¿Cómo?
No me quiere dejar hablar. He doesn't want to speak too much about him because it confuses him. So I shall only read some lines who were written when he obtained this field medal in '94. It says, he made truly fundamental discovery cutting across many disciplines, pure and applied, and his publications are so numerous and varied as to defend any easy classification. Keep in mind that there is in truth no control core, flow, or nonlinear partial differential equation, nor can there be. The sources of partial differential equations are so many physical, probabilistic, geometric, etc., that the subject is a confederation of diverse sub-areas, each studying different phenomena for different nonlinear partial differential equations by utterly different methods. Pierre Louis is unique in his unbelievable ability to transcend these boundaries and to solve pressing problems throughout the field. So these were the words spoken by Professor Evans in '94, and I can tell you his continued work after almost 25 after that has proved to be this really true. He continues to use a variety of mathematical methods to solve problems in the real world, and he is really amazing in doing so. He has had a very great success in all these branches, and he continues to produce enormous quantity of mathematics to solve problems. That's all.
Finally. Thank you. Okay, thank you. Don't believe what you said. She is a friend, so that doesn't count. Yeah, I owe all of you lots of apologies. First of all, for not being able to stay a long time, just for a very short period of time. But I have difficulties at home with my mother, and I have to teach on Friday. So, I mean, taking into account all those constraints, make the trip very, very short. I also apologize for not getting a title. And let me confess, the reason is that until essentially last Friday, I was not sure. I prepared 3 talks, and I didn't know which one to choose. I couldn't choose both. And finally, my computer chose for me because it broke down. So that's a substitute computer, so I had no choice. So it didn't break down, it went berserk. You know, without doing anything, Windows open in my computer, very, very weird. I mean, it became an independent or autonomous life form. So anyway, I'm going to use parts of an old talk and so on. So I apologize for, I would say, 3-4 people who have listened to a great portion of the talk that I'm going to give. I'm going to talk about min-field games. So most of you probably have no clue what min-field games are. I'm not sure they will have a much clearer idea by the end of the talk, but that's another matter. But it's a relatively new subject, except that it has been around for about 12 years, but still, of course, not so well known. Main-field games, I will explain later what it means. I'm going to start by showing you a little movie. Let me explain why this movie. This is a movie which apparently has nothing to do with mathematics. And it was shown to us to us meaning the group that works on main-field games in Paris around me, and especially my old friend, collaborator, colleague, and co-inventor of main-field games, namely Jean-Michel Lasserie. So engineers, telecommunications engineers want to use main-field games for many type of applications, and they showed us this little movie that I'm going to show you now. I'm going to try to show you because I don't know this computer, and everything gets complicated. Okay. Edition. Okay, so I don't know how to do it on this. So you see what is this? It's a short movie showing an intersection in a town in the south of India, and I found this absolutely fascinating. So you have cars, buses, mopes, some crazy people are trying to walk across. Fortunately, no accident. But what's absolutely amazing is that it works. Okay? So now you have this jam, and it's going to solve itself. It's absolutely amazing. Okay. So why do I like this movie, and why do the engineers showed us this movie? Because it's a good example of decentralized intelligence. You have lots of agents, very little coordination, but still it works. While, as we say in France, if you were to put some centralized, between quotes, intelligence, because I'm referring to a policeman, so if you put a policeman in the middle of an intersection, what we say in France is that everything immediately gets completely blocked. Okay? So I'm sure in Mexico, in civilized countries like France and Mexico, we share this time of slightly rebellious attitude towards police authority. Okay, anyway. Okay, I don't claim that I'm going to give you mathematical tools to explain that, but I want to insist on two ideas. Decentralized intelligence, lots of agents, would certainly anticipate because they don't want to be run over by a bus, try to optimize because they want to cross the intersection as fast as possible, interact with all the others, and have quite a variety. Okay, so that's a message. Time to begin the lecture, and I'm going to show you some more movies at some point. You will get really bored with all that mess. So, introduction, really simple examples, and then we'll see. Boss. Sir, yes, sir. What time should I stop? 10:30? 10:25? 40? Oh my God. Think of the audience, poor people. I mean, they have to get stuck here until 10:40 and listening to this guy? Okay, so, okay, let's make it short. Don't listen to her. Although she is the boss, yes, boss, I'll do what I want. Okay. So, in fact, don't read what's written. It's irrelevant. What are main-field games about? Those are models, new mathematical models. In fact, they are going to lead to all kinds of new set of equations. And in the end, I'll show you something that I prepared without a computer, namely with my hand. Then I took a picture with my phone and I show you a big diagram of all kinds of models, how they are connected all together. But anyway, it's a new class of models which attempt to describe the average in mean-field sense, and mean-field is an expression which arises in statistical mechanics, statistical physics, and which is a very simple idea that things average out when you have lots of particles, if you want to simplify the message. And this is a very basic idea in mechanics and physics, which leads to all kinds of equations from Boltzmann to Navier-Stokes, heat equations. All those classical equations of physics and mechanics are indeed mean-field equations. You average out the behavior of all the particles, except that now there is this again. So instead of particles, we have agents. Okay? So it's a mean-field theory for in a game situation. Game thought in the sense of Nash equilibria. Okay, I will remind you what are Nash equilibria on the very simple examples. So it started in the early 2000s with Jean-Michel Lasry, although I should say that there was some independent introduction of a very particular class of MFG models by Huang, Keynes, and Mallarmé. And then in some sense, whenever you have an idea in terms of modeling, you can always find ideas of a similar kind that appeared before. And here I want to mention some particular case which were introduced by economists or in game theory, which are called anonymous games, and which are discrete time and something which is called no common noise. There is also a very famous paper by Crusoe Smith. So you see that's why that's being mentioned. Let me try to use that. Anonymous Games, Crusoe Smith. This is an amazing paper by two top economists. In fact, I had no clue this paper existed, except that we were aware that what I'm going to explain later could be really useful for in economics. And so visiting Chicago, I went to the math department, to the economics department in Chicago. I knew the people there. I gave a talk in front of all those Nobel Prizes and so on. And they got excited. And Bob Lucas, who is one of the Nobel Prize winner a long time ago in economics, told me, Pierre Louis, you should look at this paper. I'm sure that they don't know it, but they are doing some mean-field game. And he was right. In a very complicated case, so they were just explaining some rules, making some Monte Carlo simulations, and deriving some partial economical conclusion. And this was one of the papers in macroeconomics, which was completely mysterious. And now, really, of course, with those tools, there is no mystery left. Okay, so numerous applications. Let me go back. Economics, finance, social network, crowd motions. I will give you some example. And every week now, it has become a fashion. Every week I discover articles using mean-field games on practical problems. So I mentioned communication networks. There is a huge literature using mean-field games on communication networks. Last week I discovered that someone told me, there are people using mean-field games on cyber criminality. I Googled it. I found immediately 12 references on cyber criminality and mean-field games, groups of attackers. So basically, let me go back, lots of applications, that's it. In fact, I was astounded to realize that the DoD in the United States proposed a MURI, those are those huge grants they're offering to universities, and the only one in mass this year is specifically called mean-field games. So I have to confess, and I realized there was a study involving doctors and mathematicians on vaccinations and so on and so on. So I could go on and go on in applications. I cannot be sure. So let me be honest. It's fun for me because I'm started in some sense this field. It's fun for me to see all those applications. I have no clue if those applications are seriously done, well developed, or is it just a fashion and so on. So one should be very careful. Right now, what I can certainly attest is that there is a huge activity worldwide in very, very different scientific and technological groups. Okay, so we'll leave this aside. I'll show you some movies later on. Yeah, I should certainly mention data analysis and so on. Okay, so let's try to go a little further in the presentation. I already mentioned combination of mean-field theory and motion of Nash equilibria. Okay, so Nash equilibria, I'll get back to that later on. But I want to insist on the point in that each player, so basically those models will attempt, and you will see a very simple example later on, will attempt to make a model of the behavior, of the average behavior of a group of people, of agents, of players, whatever you want to call them. So what are the assumptions? Is that first of all, each player is relatively small compared to the multitude. Think of an economical situation in a country, except so maybe from the owner of Telecom Mexico. I don't remember, Carlos Sim, right? That's, okay, maybe that would change the situation if he was in the picture or not for the economics in Mexico. But for the normal people, they are taken into account or not, doesn't change anything. So most of the agents are small, and there is this idea that we'll be looking at situation unless specifically explain at situations where all the players are small, anonymous in some sense, to use the economical jargon. Seven basic assumptions, and then there is this toolbox of modeling, and then possibly mathematical analysis and so on, is that each player is supposed to be rational. So the word rational is very ambiguous. So it's rational in the sense of economists, which means that they are trying to optimize something. That's what rationality means. This something may be, I want to behave like my neighbors. Herd behavior. This is supposed to be rational because it's an objective. Okay? This doesn't mean that we are naive. We know that the rational hypothesis is something which is a very crude approximation of reality. So there are various ways. We have investigated variants of model which use, as one says, limited rationality or bounded rationality. Or even you heard about the last Nobel Prize in Economics about the irrational behavior. In fact, you can see, he is also proposing, which is related to time inconsistencies, and there are ways to try to make models like that, where basically you are oscillating between two criteria, oscillating in the sense to be specified, one which is on a very short-term period, you want some short-term satisfaction, and a more longer term where more planning is involved. And how to combine them, that's, since you have two time scales, there is a time inconsistency, so it's not rational in the usual meaning. So lots of variants, I don't want to go there now. So rational small agent. And the type of feedback loop you have is that, of course, the community has an influence on each agent because he wants to optimize his behavior in a situation which is created by a community. And of course, if all the community is made of people that have the same type of preferences, otherwise you need several communities, then the action that each player chooses will make the community evolved. So community is involved in defining the action of each individual, and the dynamics of the community is the results from the individual decisions. So there is this feedback loop that we will see later on. And some ugly equation. Okay, lots and lots of models, and that's it. Enough blah blah. Simple example. Okay? Simple example, so usually I say, if you want to have an idea is, we want to go near the sea to the beach, and the question is, where are we going to put our towel on the beach? So there may be places of interest for French people, and I guess that Mexicans are not so different. It's a place, it's hot, place where you can have a drink, eat an ice cream, and so on. So that's a place of interest. And then there are possibly lots of people on the beach. Okay. So what does that mean? Does this mean that there is a certain space, you have n players? This is a very classical game, which doesn't need our mathematical theory to be solved. People knew that in game theory for a long, long time, the n player situation. So n players choose, each has to choose a position where to put his towel, xi, according to a certain criterion that depends on the others. Because basically, usually you don't want to put your towel at a location where there is already a towel, okay? Just to give an example. So it depends on the others. So it's a criterion that involves the positions for the others. What is a Nash equilibrium? It's an equilibrium, like a fixed point situation. If you fix n-1 positions at this equilibrium, the remaining position should be a minimum of its corresponding functional where you have frozen all those guys. So you see, here is a mass definition. Sorry about that. This is an equilibrium. If whenever you fix an index, the corresponding point should be a minimum of is functional, the ice one, where you have frozen all the positions. So this is the idea, very natural idea of Nash equilibria. This is a beautiful, I mean, everybody has heard about Nash as a mathematician, but also because of a movie on Nash life some years ago. But Nash wrote maybe a 2-page paper. Maybe it was 3-page on Nash equilibria, and it was a little bit of mathematical analysis. And he got the Nobel Prize of Economics for this 2-page paper. The notion is simple, but someone had to think about it. Well, however, lots of difficulty with this notion. Non-existence and non-uniqueness, crazy equilibria, and so on and so on. The question we are going to raise, and we are going to answer yes to the question simpler, is when you let the number of players go to infinity, could it become simpler? Exactly as if you are interested in the air in this room, if you want to follow all the air molecules to simplify. There are various gases, so you would have to decompose in terms of all the molecules. All the atoms, so in the end, if you are just interested in that force, which would be natural for fluid mechanics, all the motions of the electrons in all the particles and so on, you cannot do that, okay? Anyway, ODEs, think of we still don't know if the solar system anybody is stable or not, or will there be a collision? We don't know. This is a very simple question, mathematically. It's a system of n differential equation, and we don't know. Maybe in hundreds and hundreds of thousands of billions of years there will be a collision. We don't know. And so why? Because n is not huge, and those are ODEs, but they are very difficult to track down. One cannot do the mathematical analysis, and numerically there are huge computations which are being made to test as accurately as possible numerically stability of the of our solar system. So just to give this example, in quantum mechanics, as soon as you reach 3 particles, let's say 4, if you can get rid of 1, it becomes intractable. So n finite can be, especially if n is not small, can be extremely difficult. On the other hand, if we look at this all, and we want to understand the motion of air in that all, or we want to understand the temperature, how the temperature in that all will evolve in time, we have models for that. They are called heat equation, Navier-Stokes equation, and they are going to do the job. Because somehow, thanks to mean field theory, we are able to create, scientists were able to create mathematical models which gives a good description of what's taking place. So the question is, can one do the same thing in a game theoretical question? And the answer is yes, and that's exactly what mean field games try to achieve. So in distinguishable players, you have to make an assumption, exactly as in statistical mechanics, statistical physics. If you have n particles and all those particles are extremely different, I'm not talking about the mass, I'm talking about, you know, the properties. There is nothing you can do. There is no simplification. When you write down the equation, you're saying that the medium is homogeneous. When you write down the Navier-Stokes equations, you're using implicitly the fact that locally there is thermodynamical equilibrium, etc. So this means indistinguishable particles. Same thing, indistinguishable players. So what does that mean? This means that if we go to the beach, we can change our name tag. You know, suddenly, you will be called Lions, and I will be called Caballeros, and we can't change anything, okay? So that's this possibility of exchanging the role of two players is exactly what is meant by indistinguishable player. So what you're saying is that this criterion that depends on all the others depends on my choice. I'm xj. So that's my choice, that depends on my choice. I want to be near this place of interest, okay? And it depends on all the others. But view from this guy, view from my perspective, all the others are the same. I can exchange a name tag, they don't change anything. So it's a function of one variable, and of course n-1 other variables, but this is a symmetric function of these n-1 variables. And of course, I play the same role than the other, which means that this function f for me is the same as the one for her. So there is a single f. So this is more structure. We still go back to the usual difficulty with Nash equilibria, still there even with that structure. You may have crazy Nash equilibria, non-unique, blah, 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 and doesn't help much. However, it will allow to pass through the limit as n goes to infinity. Of course, you have to change point of view slightly, mathematically, very simple, because clearly here we have a function of n variables. So the setting in which we are looking at the criterion changes with n. So the first step is to try to have some fixed mathematical framework which doesn't depend on s. And the way to do it is to replace points. When you take a bunch of points and you're looking at them, you have the identification. It's really a quotient space, but let's not use complicated words. We are just looking at them, and we may make exchange. It doesn't change anything. You know, exchange the tags of all those particles. Then you can replace looking at n-1 point in a symmetric fashion by looking at the empirical density, empirical distribution of those points. In other words, building this probability measure, which is 1 over n-1, the sum of the Dirac mass at xj. These contain the same information, except now I have, for each n, I have probability measures. I have a framework which is independent of n. There is a part of the mathematical theories which exist is about letting n go to infinity, and this is just explaining why certain functions which are symmetrical in n-1 variables are in fact asymptotically functions on the space of probability measures. Then you move into differential calculus, where how does the differential calculus in Rn is lifted on differential calculus, partial differential equation in Rn are lifted in partial differential equation on the space of probability measures. This is just the first step. Just looking at points, replacing by probability measures. And then there is, once you have done that, then there is the whole, you can redo all analysis behind. Okay. Fine. If you admit just this simple change of perspective, then you can prove a theorem which says that all Nash equilibria converge as n goes to infinity to solution of what should be the mean field game for this very particular problem. So let's stop there, let's breathe a little bit and look at what this problem is. So the unknown is a probability measure. So what this model is going to provide is not a recipe to where to put, telling you where to put your towel. You know how to do that. You don't need any kind of mathematical theory. But if you behave in a rational fashion, maybe we can predict the outcome of all those individual choices. And the outcome will be the repartition of towels on the beach. I don't care about towels on the beach. I'm just giving this as an example. Okay, so that's this M. So the new unknown is a priority measure. Mass equilibria, you fix all the other players. This means M. Because of course, I am among the community, but I weigh nothing in front of infinitely many players. So I can forget the fact that I'm part of it. So fixing all the others is fixing M. In physics, it's ignoring the self-interaction. So I fix M. And then I want to say that all the players have to be minima. A generic player has to be a minimum of the function of the remaining variable. That's the idea of mass equilibria. What is a generic player? Well, that's any x in the support of the measure. So outside the support, M is 0, there are no players. So you see that this is a non-standard optimization problem. For any fixed M, you have to maximize, you have to minimize, that's a media optimization problem. You get a set of minima which a priori depends on the measure M, and the equilibrium, the fixed point condition, is that the support of M should be included in the set of minima of this function. Okay. Then, thanks to the fact that priority measures, a set of priority measures is essentially compact if you have the right topologies, weak topologies if you want, and you have general existence and stability results. There is something that I want to explain in a minute, which is uniqueness if F is monotone. Okay, I'll go back to that. Also, if the force comes from a potential, the force is really the criterion. If it comes from a potential, namely it's a derivative on the space of priority measure of a certain scale of function, then through this global optimization you can yield one solution. So this is typically called decentralization or planning in economics, where you have a game situation, but it turns out to be equivalent to a global optimization. So the Eden hand of the market and stuff like that, okay? So there are lots of, but this is a very, very particular situation, as we will see, and it essentially requires to have some kind of gradient form, which is rare. Okay, so monotonicity, the role of monotonicity. So there are low notations, but believe me, I tend to believe that this is very rudimentary. Let's give an example. So those are the preferences of the ice player. Location, where does he choose his location? That's how he measures his preferences. And this expression will reflect the fact that I want to say I don't like to be in a place where there are too many people, or where there are many people, or on the contrary, I like to be in a place where there are many people. Okay? So how do I measure that? That's a little bit of modeling. Well, I'm going to count. So I'm sitting at point xi. That's for my finger. That's complicated. And I'm going to look in a certain radius, and I'm going to look at the frequency, both in terms of numbers and spatially. So typically, I'm counting the number of people in a given neighborhood. And you see it depends on the type of applications. If you're interested in a towel, so the typical radius would be 10 meters. If I'm interested in all those things, it may be a different scale. Okay, let's forget that. So this is now a criterion. Let's not waste too much time. This is a criterion which depends on endpoints. This is the version on the space of priority measures, f of x And the function of the measure is this G function, I've not yet explained what is G, of the convolution of the probability measure with the normalized indicator function of that ball. So in particular, if you want to idealize this, you let epsilon go to 0, and you have f of x plus g of m of x. So what is G? So here I'm counting how many people are around me. So if G increasing and I want to minimize, this means that I'm averse to having too many people around me. That's not good. On the other hand, if G is decreasing, this means that as I usually say, normal people tend to avoid very crowded places. But there are abnormal people that really want to be in crowded places. They have a name. They are called teenagers. So that's my usual joke here. I mean, I know 2 or 3 people that have heard it about 3 or 4 times. And one is still smiling, the other one not. Okay, so, but anyway, and G is going to measure by being increasing or decreasing whether I want to be in a crowded place or not. And so if G is increasing, that's monotonicity, it's an increasing function, there is uniqueness. So in particular, there is a single equilibrium if everybody wants to drop its towel with some individual preferences and wants to avoid being in a crowded place. There will be a nice repartition. On the other hand, if it's decreasing, there is no uniqueness, and you can understand that. Because suppose that you have 2 places of interest, equal interest. The drinks, the beer is the same, the ice creams are the same, it's fine. So clearly, and people want to be together. There are 2 solutions. Everybody is going to group around one point, or everybody is going to group around the other point. That's 2 solutions. And in order to decide by those 2 solutions, this is not min-fit games. It's fashion, it's something else. You have to, and you can have symmetry breakings and so on. I mean, this is something else. Okay, so I wanted to explain that. This is a very natural. Okay, so this is a very simple example. What do we learn? Forget about towers and so on. We learn that by switching our point of view from endpoints to probability measures, the price being paid in terms of having now problems, equations which are set on the space of probability measures, if we are willing to pay this price, then there is a way to set up limits, at least formally, and one can justify this in many cases, although this is hard mathematical work, one can set up models, equations, which are at least partially posed on the space of probability measures. I'm going to show you one example of such an equation in the space of probability measures. It's going to be an equation that it's really awful, okay? So I don't want you to have nightmares tonight, so please be careful when looking. Parental guidance, PG-13, I would say. Okay, so here is the equation. I don't expect you to say, oh yes, of course, but you forget a term in the second line, which is plausible, by the way. I will try to explain. So first of all, what I want to emphasize is that we're going to switch to a dynamical problem with a finite horizon t, continuous time and space. The noise is going to be very simple here, Brownian noise. Okay, now we have each player is submitted to random events called Brownian noise, and they are indistinguishable. So what does that mean? This means that there are only 2 options. It's always a combination in such a situation of one common Brownian noise and independent Brownian noise from one player to the other. There are no other possibilities because of symmetry. That's a trivial observation. Okay? So in what I'm writing, the nu corresponds to the amount of independent noise, while the alpha corresponds to the amount, roughly speaking, of common noise. The value function is now a function that depends on x. I have to explain what x is. M, probability measure, that's the state of the community. So all states are possible, and given a state and a certain objective, I need to understand what is the best possible value I can have for the community, and that's a U function. that depends on X. So what is X? X is a bunch of variables which are the description of each player. It could be its age, its position, its wealth, whatever. So you list, that's for model making, you list in X how you're going to describe the state each player is in. Okay? In particular, I won't do that, but it may be in a situation where X itself is infinite dimensional. Because it could be an history, a past, it could be an histogram, a measure, and so on. In which case, the M is a measure of measures, but I don't want to go there. Although I will introduce another point of view which makes this type of extension not more difficult. But anyway, so there are a bunch of Laplacian that's found in motion. There is something which in X looks like a heat equation, except it would be more like a Bellman equation. This part of this is is very much reminiscent of Hamilton-Jacobi-Bellman equation, which means that they are the controls on drift only. It's a pure Laplacian. The criterion only the criterion depends on M, and there is no intertemporal preference rate. I will come back to that later on. So then that would be, if there was no M, that would be a pure Bellman equation, which is optimal dynamical control. It's well-known equation that corresponds to that situation. Except now everything depends on the others, and whenever I choose by optimization a certain policy, it will affect how the group evolves, the community evolves. So that's why you have derivatives with respect to the probability measures. So those are first and second order derivatives. I don't want to discuss, but this is the effect. Each player chooses, and its action make the measure move, and thus the best possible value function for this has to move as well, and it moves by reacting with such terms. So you see the two parts of the equations. One is about choosing, and the other is if everybody chooses, this makes the community moves. So this is an equation which looks like nothing in terms of equations. First of all, it's infinite dimensional. Second, it has no particular mathematical structure which had been identified previously in the zoology of partial differential equations. You mentioned this quote by Craig Evans saying there are so many cases in PDEs that you can't expect to have the global unified theory of PDEs. That's true, but there are still big classes of PDEs for which you have big unified theories. And this one didn't fit, and still doesn't fit in any classical branch. Plus the fact it's written down in the space of priority measures, and writing down derivatives in the space of priority measures is a dangerous game. Okay, let's move on. Okay, so I want to mention two particular cases where this infinite dimensional problem gets simpler. One is a situation where there are only independent noises, so each player has his own random events, independent from one to the other, and are not submitted to a common noisy background. In physics, usually when you have interacting particles, they may have independent noises. In biology, in economics, and so on, there are shocks. There are things that affect everybody. So this is a very strong assumptions, but not the only case where we can reduce it in a purely continuous fashion, in a purely continuous setting. Independent noise is the only case where, where am I? Here. Where we can write down a system equation in finite dimension, which is linear integration along characteristics in M, too technical, which combines some kind of Bellman equation and some kind of Fokker-Planck equations, the two being really coupled. And it's a forward-backward system, and this I want to explain. Fokker-Planck is description of the evolution of the community. That's forward-looking, although I changed sense of time here, but forget it. Because we are just following the history of the evolution of the community. Binary equation, it's about choosing, it's about controlling, it's about decision-making. Decision-making, choosing is always about anticipation. There is no way you choose without anticipating, at least for some period of time. So this is naturally backward in time. Okay, so that's why you get some kind of heat equations, the extremely nonlinear heat-like equation, but one is going forward, the other is going backward. It contains many, many classical equations that I wrote down here, but that's irrelevant. Okay, the other example that I want to describe is the case where the variables describing the state of each player are discrete. So it's a finite state space. Finite state space means that to describe a player, I'm just having to say that it is in site I. That's all. Okay, that's discrete. But there's still M. M is going to be the repartition, the probability density, so the histogram of how the various people are in, how many are in site 1, how many are in site 2, and so on. So there is still M. And those are continuous variables. Okay? So the X now stands really for the M in the discrete space. And in a finite state space, what you have is a system of equation which is in the terminology, in the PD jargon, it's called a non-conservative hyperbolic system. So essentially nothing is known, period, on such systems, which has, however, a very particular structure, but that's too technical. So it's a non-conservative hyperbolic system. So the only advantage, although it brings a class of equations for which there is nothing in terms of general results, mathematically speaking, at least it's finite dimensional. Okay, so that's the only interest for the time being. Okay, what do I want to say now? I want to mention another point of view. And that's a very important way to argue, is to say that instead of writing down equations on the space of measures, I can write down equations on the space of random variables by identifying a function on the space of probability measures and functions of random variables. I want to look at functions of random variables which depend only on the law of the random variables. So it's automatically a function of probability space. And I can always rebuild. So this is an identification. It's exactly as saying if I have a function of two variables, I can either look at it, and it's symmetric in x and y in exchange. I can look at it as a function of two variables, or I can use a quotient space, x, y, quotiented by the equivalence relationship, and say I have a function on the quotient space. So you lift it to random variables and probability measures, that's exactly the same thing. And this is not a simple, it's a real analogy, it's more than an analogy with what I just said. So it turns out that when you do that, the equations becomes much more like now in an Hilbert space, if you have random variable with second moments, you write down non-PDEs in a Hilbert space, which look very much like the hyperbolic system I wrote a minute ago. Okay, look, FG, let's move here, FG, right? Except now X is a random variable and U is a mapping from random variables into random variables, which is equivalent. I don't want to get into that. So, okay, so there are ways to look at those things. So in fact, this means that when we look at a function, a symmetric function of n variables, we have three ways to look at it. We can look at it as a function of x1, xn, which is symmetric, the usual way. We can look at it as a function of the empirical measure, 1 over n sum of the delta xi's, or we can look at it as a function of our random variables, at least those random variables that takes only values x1, xn with probabilities 1 over n. Those are 3 points of views which are completely equivalent. And of course, when you lift them as n goes to infinity, you have the various point of views that I'm mentioning now. And mathematically, from the analysis point of view, if you can work in an L2 space, you have now a linear structure, so you have classical differential calculus. And if the functions depends only on the law, you still keep the compactness of probability measures. So it's almost as if you were working in Rn. Compactness, flat structure. Okay. Which explains why the theory developed a lot. I should mention that recently René Carmona and de la Rue wrote a collection of 2 books. It's 1,500 pages long. It contains about 30% of the mathematical theory of min-field games. That's my estimate, just to show you how much the theory has developed in 12 years. And they developed much more the probabilistic approach to those questions, which is something that I'm not really addressing. Overview and perspectives. How am I doing on time? I'm okay. So instead of doing that, I will finish with 2 simple examples. So believe me, even if you are a little bit lost in the PDEs, you can try to wake up now. It's a good idea because now it should be easy. So the difficult part is over. So let me try again computer problems. Fine. How do I do that? Okay. So I want to mention that one application is about evacuation. In fact, the people in charge of building the highest tower in the world, worldwide, in Abu Dhabi, have given out a contract to a group of engineers for the evacuation of floors of such towers, because when you have those monster building, if there is any problem, how are the people going to be evacuated? People use more and more mathematical models and numerical methods. So MFG are being used. It's a crowd motion, and here I'm going to show a few examples that we did just for fun. I mean, it's just a pedagogical. So you think of a movie theater. So you have rows. You see, you have rows. So these the blocks represent the number of people, and you have various rows. And the doors to get out are going to be at the bottom. So simple MFG model. You don't think too much about modeling, and you look at that, you have little peaks forming at the end of the rows, completely symmetrical evacuation, 2 doors, nothing much. If you look carefully, you say, well, there are things which are not realistic there. Part of the thing is that one is not taking into account a factor which is that people cannot really tramp on each other. They cannot walk on each other. And so you have much more spikes at the end of the rows, and that's in terms of qualitative behavior, that's much better. And then we made a more complicated situation, which is a common shock, so common noise, if you want. So people know that at a certain given time they will have to get out. And the only thing they know is that they can see 2 exits. But they're going to discover that one is blocked. And they don't know which beforehand. Okay? Which is not so unrealistic. This kind of shit, sorry for the expression, happens. So symmetrical. Okay, it's building up. And so you see, of course, the exit is of course the one on the right. So those are just pedagogical examples which shows what is how the toolkit can be used. Then you can start to discuss. Then we are still very far away from the movie I showed you in the beginning for the intersection in India. I'm perfectly aware of that. Although the main, we can we can obtain the main phenomenon. I want to show you something. Okay, so that's homemade with my, except where it is. Let's see. So I told you it was homemade. Okay. So it took me 2 hours to do that, and the result is just disgusting. But anyway. Okay, so the master equation, Winfield-Games equation on space of priority measures, if the number of, if the size of the community is not fixed, then you have bounded measures, not m, or in input space. When it comes from a gradient, you have Hamilton-Jacobi-Bellman equation on Pm or H. The two cases I mentioned, independent noise, so the finite dimensional problem, hyperbolic system, forward-backward Winfield-Games. All this comes from Nash equilibrium as n goes to infinity. In fact, there is questions in physics which give rise directly interacting particles with enlarged deviations, which give rise to problems of that type. Okay, in the potential case, this becomes a Hamilton-Jacobi-Bellman equation. In the case of independent noise, as method of characteristics, it becomes forward-backward ODEs. And if you do that, now you reverse the order of, you now use independent noise on this, and what you get are forward-backward, completely general Hamiltonian system. There is a bunch of arrows which are called lambda goes to infinity. I want to mention that because it's very natural. Lambda goes to infinity is, lambda is a parameter which is going to measure the intertemporal preference rate. So this is going to tell you how much the future counts now. So clearly what happens in a year from now may count, but maybe a bit less than if it were happening today. So that's the role of discount factors, intertemporal preference rate. When it's very big, it means that the future counts less and less. You become much more myopic in your anticipations, time-wise. And so when lambda goes to infinity, you become blind to future anticipation, and you just react immediately. And that's called, if you were in a finite state space, that would be called an agent-based model. And if you have a continuous system, that would be kinetic models. And so this limit lambda goes to infinity that we worked out recently from master equations gives kinetic stochastic partial differential equations. At Nash equilibria, it becomes n interacting particles. That's good to know. Finite state space, it's ODEs or agent-based model. You see that all this makes sense. Lambda goes to infinity with independent noise. This becomes kinetic PDEs, deterministic ones. Here, there you have noise, Brownian, or jump, or whatever. Okay, this is more or less the global picture, which is not of all PDEs, but it contains lots and lots of PDEs, which are about the description, always. What do they have all in common? Is that you are trying to describe a group of particles, a community of particles, a community, and you have one part of the diagram, the upper part, which is about decision making, and the lower part is we react mechanically, okay? Like physical expressions. Okay, so I wanted to show you, so you see how this global picture of trying to make models for the evolution of a community, how this picture is organized, at least in my mind. Some people may disagree with such type of organization. Okay, time to finish with two simple examples. I won't be talking about big data to try to, I'm not going to be ranting against big data today. You will escape that. Although I don't say, well, anyway. Okay, so many things. Two more S examples. S stands for simple, but it stands also for silly and stupid. So I think this is a very good way to ask you to listen to what I'm going to say now. One example is at which time will the meeting start. So here is the rule of the game. A bunch of people have to go to a meeting. They don't really know how long it will take to go to that meeting because they have to use public or private transportation in Paris, for instance. So I suppose that Mexico City wouldn't be that different. So you're not totally sure to make it in time. Plus the fact that if you're in a civilized country, the meeting won't start exactly on time. And okay, it may look good to be there on time because for those who have been on time, it looks slightly bad to be there, a little bit late. Okay, so there is a little cost of being late, and there is a much steeper cost if you get there after the meeting has started. Then you really look bad. When does the meeting start? When enough people have arrived. Okay, like for 80%. That's a minifield game. So you translate this in a minifield game situations, and you can make numerical computations, somewhat explicit computations. You have various parameters, and even physicists have looked at it from a phase transitions point of view, depending on the various parameters and so on. Physicists are now working a lot on minifield games. Okay, so that's an example. But I prefer, being in Mexico, I have to talk about the hola. Okay, so the hola in America, in Northern America, in the United States, is called the Mexican wave. You know what the hola is? Okay, good. You know where it started? It's called the Mexican wave. You should know that. Now, come on. Even if you didn't know, you should guess. You're asleep. Okay, the hola. Yeah, indeed. This. You're about 100,000 people. They are not being paid to do something silly like that, and they do it, and the wave goes on and on in a very stable fashion. It started in Mexico, indeed, during the World Cup. We were discussing with some football experts. Football, we are in Mexico, we're not going to say soccer. Football experts, so I already forgot. I mean, it was a World Cup 86. Okay, so first hola was invented here. Okay, there's been a lot of scientific studies about the hola. Don't prove much. Now, given any subject, you will find thousands of references on any, even completely stupid subjects. Think of minifield games. Well, anyway, so in fact, I wrote, if you want to have some fun about statistics and big data, I do recommend reading the article in the New England Journal of Medicine, which is called Chocolate, Cognitive Functions and Nobel Prizes, explaining the high correlations between eating chocolate and getting a Nobel Prize. So that's a good example about big data. But anyway, where was I? Mexican wave. Mexican wave. So it started, and those people do it, and it works. So there is a spontaneous, synchronization of lots of agents. So it's a very interesting phenomenon, and that's why there is a lot of literature. There were lots of interesting experiments, because if you, the hola always goes clockwise, okay? So, in fact, I remember asking some friend from Argentina, asking him, maybe in the southern hemisphere it goes anti-clockwise. So, and the guy told me, yes. I got completely excited, and the day after it said, no, always the same way. So it has nothing to do with water in the sink and so on. Okay. So, however, about counterclockwise, there was an experiment made during the Olympic Games in Sydney. So they made an hola going anti-clockwise. It was stable, going at the same speed. Oh yeah, I forgot to say that. The speed has been measured. It's always the same speed all over the world, okay? So it's a reproducible experiment. So then it makes some sense to try to have some kind of scientific explanation. I'm not saying that mean-fit games is the right explanation. In fact, what we were really interested was in the propagation of crises, of shocks in economics or financial situations. But we wanted to avoid controversies with economists and so on, so we claim that we were studying others. To be happy, stay hidden. So how does our model work? And I'm going to stop in 1 minute 40. So I'm obeying the boss. Huh? I'm just late. The idea is the following. This is how the toolkit functions. So in a given row, we are going to say there are 100 people, that's a lot, and we're going to take a probability measure on a row. So you will have two variables, the state in which one people is in the row, the generic player in the row, and the position of the row along the circle. Okay? Those two state variables. Assumptions, modeling assumptions. Moving is an effort, kinetic energy. You throw that in your Lagrangian. Position has a cost. Standing, I'm going to be ridiculous, I know, but just a little bit more. Standing is comfortable. Sitting is comfortable. In between, that's not okay. That's uncomfortable. So you have a cost function for position, which is highly concave, and which tells you that in between 0 and 1 are fine. 0 is sitting, 1 is standing. In between, that's painful. And then, final term in the criterion, I want to be in the same state than my neighbors. Okay, herd behavior. So you measure that, you make a local average, that's it. Okay, so you have two parameters. You crank the toolbox, modeling toolbox, you write down a model, you do some mathematical analysis, which is fun there, and you make a prediction. If, so you're assuming that all stadiums are basically the same size. If the coefficient in front of the term I want to be like the other is not too small, then there exists a unique periodic solution. Okay, it's unique, up to clockwise, anti-clockwise. So you have two solutions if you want. Unique stable. So in particular, it always has the same speed. I'm not saying it's a good model for the OLA. I'm just saying that I made some assumptions on the behaviors, and I make a prediction which is consistent with what is being observed. Then, if one were serious about the OLA, one would need to make measurement, to try to explain some transitions, why it breaks down, and so on. I'm not serious about the OLA. I just wanted to make, on this example I don't really believe in, who knows, but as a pedagogical example, how one uses the toolkit. Okay, so mathematically, I said there are two examples where you have finite dimensional equations and you have this infinite dimensional problem. In fact, and I showed you with the equilibrium for towers and places of interest, I told you if I don't want to be in the places where there are too many other, where there are too many people, monotonicity, then problems there are unique solutions. And that through all over the diagram I showed you. It's a complete general feature. In some particular models, you may have further uniqueness because you have a specific structure. But at least you have this. And the other piece of information I want to mention to close is that at least as a short-term, short-horizon problem, it's always well-posed. There is always a unique, smooth solution. It's like Cauchy-Lipschitz for ODEs, if you want. Except that now it's infinite dimensional, it's a mess, it's complicated, but it's well-posed, like ODEs are well-posed. So at least we have those things. There are lots of open questions, that's why there are, many and many mathematicians worldwide that are working on this or that aspect and so on. But just on one of the breaks I mentioned mainly the hyperbolic system, and part of this is my fault because the only material can be found in videotapes of my courses at Collège de France. So I use this excuse not to write this part. And so if you want to have some more details about that part, you can download the tapes, which are usable. Some of my students have really worked and learned the subject on those tapes, and you can watch them. Well, especially if you have troubles sleeping at night. So I can recommend it. 10 minutes, you will be sleeping. So thank you very much.
So, questions or comments? Ya no sirve esto.
And also, if there is always a possibility of asking me directly questions.
So the general theorem of Nash says that normally there is a mixed equilibrium and not necessarily a pure.
Yes.
And here I got the impression that in your case it always corresponds to a pure equilibrium. Is this indeed the case?
Okay. Except that when you let the n go to infinity, the difference blurs. Okay, so that's why I didn't look in the position game. It has a very specific position game. I mentioned it has a very specific structure. Although existence may be a problem in some situation depending on the type of criteria. So I'm not too concerned about that. But when you let n go to infinity, the notions of pure or mixed strategy, the difference gets blurred, and is blurred. So you forget about it. We see mixed strategies popping back when we deal with things which have a more 0-1 nature. And here I'm thinking about min-field games with optimal stopping. And there will be indeed mixed strategies which appear very naturally. But if we are in a purely continuous situation, the framework forgets about the difference. And one has to see it by introducing more discreteness in the system, and optimal stopping, choosing a time where people can leave the game, and some others may come, is a situation where mixed strategies have to be looked at. And so it's more in the context of mixed strategies overall.
¿Otras preguntas?
So you talk about the case when the number of players goes to infinity. What happens with the time horizon also goes to infinity?
Okay, everything can be studied. When t goes to infinity, this is infinite horizon. I wrote down the equations for finite horizon. There are systems of equations which are by nature correspond to the infinite horizon problem, but they may still be time dependent in the sense that you will have an infinite horizon problem where you still have to say from which density, from which description of the community I started. So that's the general infinite horizon problems. Now, in some situations, because of ergodicity, because of simplifications, you may have stationary infinite horizon problems. But this has been studied, and we have some mathematical answers. Like in PDEs and analysis, there is never a final answer. Well, overall in maths, you can say there is never a totally final answer. But a complete description is always impossible, especially in analysis. And so we have lots of information. There are, again, thousands of open questions. But this is understood. And one has to be very, very careful in saying the infinite horizon problems are not always steady-state problems. Okay, they may be time-dependent.
¿Más preguntas, comentarios? Pues entonces agradezcamos a la... Qué maravilla.
Aquí es la música de los que se salgan.
Ah, sí. Tú.